All right, so I am sure you're still working on this. That's okay. Let's work together and finish what we haven't started. So it says that a particle is moving along the x-axis so that its velocity at any time, t greater than or equal to 0, is given by the velocity function below. The position of the function is given by x of t equals t cubed minus t squared plus minus t plus c, where the distance from the origin is measured in inches and is measured in inches per second. If we are given that x of 2 is equal to 5, determine the value of c in the position function, and then rewrite the function using the calculated value for c. So, in order to determine that value, what we needed to do was say, okay, 5 equals 2 cubed minus 2 squared minus 2 plus c, and then simply solve for c. So what you could do is take what you know and find what you're missing. We know that whatever c is, it has to make this statement true. So you should have gotten c is equal to 5. C is equal to 3 when 2 is equal to 5. Good? Makes sense? And then it says use a graphing calculator, graph that function. So when you graphed your function, you should have seen a graph. That kind of looked like it was increasing exponentially. Remember, this is a zoomed in cubic. Then it said calculate all values of t for which x of t is equal to 2.207. So how do I do that? Well, to calculate the values of t at which that is true, we're looking for two things. On a graphing calculator, you are looking for a point of intersection. So again, and actually that line would be a little bit lower because my y-intercept was at 3. So it would be down here. So you're looking for points of intersection. You could also say 2.207 is equal to t cubed minus t squared minus t plus 3. And then you could have moved over the 2.207 and set that equal to 0, plugged that into y1, and found your zeros. Or again, you could plug this half in y1, plug this in y2. And does everybody know how to find the points of intersection if something's in y1 and y2? Or do we need to walk through that on a graphing calculator? Thumbs up, you know how to find where two lines intersect. Thumbs down, you have no idea how to do it and you need me to show you. Okay, so we're all good. Thank you. I just want to make sure I don't know what you know. So you would use your graphing calculator to find the points of intersection. You should get 2 answers. So you get 0.645 and 1.3. Those 2 answers represent the time at which the particle is 2.207. So again, it says interpret the meaning found in B. So again, it means these are the times at which the particle is 2.207 inches to the right of the origin. Part D, use the information from B and C. Explain what the particle must do in order to be in the same place at 2 different times. So to be in the same place at 2 different times, the particle must change direction at least once during the time interval. So in order to be at the same place at 2 times, the particle must have changed direction at least once. In that interval, so the particle changed direction at least once in the interval 0.645 to 1.3. Okay, number 3. By analyzing the function from the table feature of the graphing calculator, describe the activity of the particle from 0 to 5. So you did second graph, go to the table, and what you want to do is tell me what is happening. So at t equals 0, we should notice that this is when the particle starts to move. At t equals 0, the particle would be 3 inches to the right. How do I know this? I know this because at t equals 0, the answer I get is 3. So what that means is the particle starts 3 inches to the right of the origin. At 5 seconds, the particle is at 98 inches. And again, I'm seeing that from the table. So at 5 seconds, the particle is 98 inches to the right. Anytime the particle is negative, then it means that the particle moved left. It only moves left from like 0 to 1. We're going to talk a lot more about all of that in depth throughout the course of this week. What does it mean when it asks you for the average rate of change? What is the average rate of change? Slope. Thank you. Average rate of change is slope. So we are literally looking for the slope from 3 to 1. So that means you're looking at x of 3 minus x of 1 all over 3 minus 1. And you should get 8 inches per second. 8 inches per second. So if it asks you for the average rate of change from 5 to 3, you're doing the same thing, but from x of 5 to x of 3. And we get 40 inches per second. So if the time from 3 to 1 is 8, and then the next time from 3 to 5 is 40, what does that mean about the particle? What does that mean about the particle? So it says interpret the meaning of the average rate of change for the position of the function over each of the time intervals. So if it's going from 8 to 40, it's going 8 inches per second to 40 inches per second. If you were going 8 miles per hour to 40 miles per hour, what are you doing? Accelerating. Excellent. So the average rate of time is speeding up. Therefore, the particle is accelerating in the positive direction. And then it says like to talk about particular things. So what that means is the particle is accelerating. It covered 16 inches in 3 seconds versus 80 inches in 2 seconds. Part A of number 5, algebraically calculate the velocity at 0. So way back at the beginning, it gave me the velocity equation. So all we're going to do is set that equation equal to 0. It is a quadratic. If you have a quadratic equation set equal to 0, what's your first decision or first move? I have a quadratic equal to 0. What am I going to try to do? Easier than quadratic formula. What? Like, yes. Yeah, I was like, I can't hear. Yeah, guys, we're trying to factor that. So it factors as 3t plus 1, 3t, or t minus 1. So that means you're going to get a negative time and a positive time. Well, time can only be positive. So that means that the velocity is equal to 0 at t equals 1. Velocity is equal to 0 at t equals 1. Describe the motion of the particle at this time. Well, if a velocity is 0, think about driving a car. If your velocity is 0, what are you doing? Your velocity of your car is 0. What are you doing? You're standing still. Perfect. You're at rest. You might be at a stop sign. You might be in a parking spot. You might be at a red light. But what that means in part A is if the velocity is 0 at 1 second, then the particle is not moving. Okay, and then the last two. So these are a little different. Part A, you had to solve. In part 6, you are simply plugging in a number. So you can do this on a calculator. So if the velocity is negative, which was kind of a key idea for today, if velocity is negative, a particle is moving to the left. And we saw that up above. We saw that in the graph. We see that the velocity is 0 between them. So typically if a particle goes to rest, it changes direction. We know that the velocity was at 0 at 1. So that is between 0.36 and 1.276. So typically if your velocity goes to 0 between them, then it's changing direction. Good? Everybody able to copy all that down? So we have the difference quotient. If you think back, the difference quotient is something we've been talking about in calculus for a while. What does the difference quotient look like? What? Yes, but there's another name for that formula. Has another name. It represents something we've been finding before the definition of the derivative, because there's no limit. So the definition of the derivative had a limit. Yes, the slope of the secant line. Excellent. The difference quotient is another name or word for the slope of the secant line. So f of x plus h minus f of x all over h can be interpreted as the average rate of change, which is the slope of the secant. Again, this represents the slope of the secant. If you take this same equation and you throw a limit in front of it, you now have the derivative. The derivative is the instantaneous rate of change. We now know how to find the derivative using the power rule, the product rule, the quotient rule, and our trig derivative rules. So we don't have to use this long definition anymore, but the ideas and the concept behind it have not changed. The instantaneous rate of change is still the limit as h approaches 0 of the average rate of change. So all we're doing as we find velocity is looking at the slopes of the linear function before it getting closer and closer to 0. So if you were to enlarge a circle or shrink a circle, we need to idealize what's happening within a circle. So we know that a circle can be stretched, it can be compressed, it can be shifted to become an oval, lengthened, etc. So it says find the rate of change of the area of a circle with respect to its radius. So area equals pi r squared. Rate of change means to find the derivative of that. And we're finding the derivative with respect to radius. So we are finding d dr. So the derivative of area with respect to the radius is dA dr. And then pi is a constant. So when you find the derivative of a constant times a variable to a power, we use our power rule. So the power is 2. So the rule is bring the power down in front. The power multiplies by that constant. In this case, the constant just happens to be pi. And then you subtract 1 away. So a quadratic becomes linear. So the derivative of area of a circle becomes 2 pi r. What does 2 pi r represent? Chase? The circumference. That was very missing. Excellent. The circumference. That is not by mistake. The derivative of area is circumference. So then the next part B, says to evaluate the rate of change of the area when the radius is 5 and when the radius is 10. So what that means is I need to find dA dr when r is 5. So in calculus, when you're interpreting notation for a derivative, so it's dA dr when r is 5, that's Leibniz notation. You could also say a prime of 5 but ultimately you are looking at 2 pi of 5. Which is 10 pi. Let's look at 10. So is the rate of change from 5 to 10 getting smaller or larger? Is the rate of change getting smaller or larger? Is 10 pi smaller or larger than 20 pi? Yeah, 10 pi is less than 20 pi, right? So from 10 pi to 20 pi, the rate of change is increasing. So if the rate of change is increasing as r is increasing, does that mean that the circle is getting bigger faster? If the rate of change is increasing as the radius is increasing, does that mean the circle is getting bigger faster as the radius is getting bigger? Chase? Yeah. So that should make sense to you. If the rate's increasing as the radius is increasing, then it's getting larger faster. If r was measured in inches and a was measured in square inches, what units would be appropriate for dA dr? So if r was measured in inches and a was measured in square inches, the derivative of a would be square inches. The derivative of r would be inches. So if you have inches squared divided by inches, you would be left with inches. If you had inches squared divided by inches, you would be left with inches. Okay. We're going to pause here. Your homework is on page 135. So you're doing the quick review 1 to 10, and then 1 to 4 in the exercises.